and welcome to another tutorial. My name is tanmay bakshi, and this time we're going to be going over building convolutional autoencoders with Keras, or generally neural network autoencoders. Let's begin. Now, to start off, what in the world is an autoencoder? Well, before I can explain that, I'm going to assume you know the basic working of not just neural networks in general, but convolutional neural networks in specific, although dense neural networks will allow you to understand this video as well. So let's begin. Now, in order to explain this concept, let's take a look at image classification. Now, when you want to classify an image with a neural network, what do? You take the image and you input it into a neural network, just like this. So what you do is you take, say, an image you've got. Alright, you'd feed it into a convolutional neural network. You'd feed that into a bunch of dense layers. That would give you an encoding, and then you'd feed this into a bunch of dense layers, which would give you your output, which is the probability matrix. Like so. That's what your architecture looks like. Now, of course, you can have an arbitrary amount of CNN layers, all the hyperparameters will be tuned, but this is really a bird's eye view on what your neural network looks like. Now, in between this step and this step over here are things called encodings. And encodings basically represent the input image in a semantic vector. And that semantic vector basically just stores all of the useful information of the image in a much smaller vector than the original image. Like, for example, we could have a really high resolution 4K image over here, but the output after this dense layer could only be, say, 1,000 individual values, one-dimensional array. And so that's an encoding. It represents everything that was in the image, with some loss, of course, because it's impossible to do that magic compression. But it represents the meaning of everything that was in the image, including things like trees, leaves, people, really whatever is in the image. However, you have to make sure that the CNN has been trained on that data set so that it has an appropriate set of filters to filter down and create the correct encodings. But what's an autoencoder then? Well, in order to explain that, let's go ahead and take the eraser here. And let's erase these layers. We're going to remove the probability matrix and our dense layers. We're just left with an image and a trained convolutional neural network. Now, the output here is an encoding. Alright, so you're outputting an encoding. Alright. So that's what your neural network has in terms of output. Now, this encoding, as I mentioned, represents everything within the image. But what an autoencoder does is it tries to decompress the compression that this convolutional neural network did. And so if we've got this encoding here, then we can decompress what's represented in this encoding with an autoencoder. Now, what you can do is you can use something called a deconvolutional neural network. Okay? Now, a deconvolutional neural network is practically, as the name implies, the exact opposite of a convolutional neural network. It basically inverses what a convolutional neural network would do and actually upscales the image instead of downscaling it. However, there are also layers like pooling layers. And so in this case, instead of using pooling layers in this deconvolutional neural network, we'll use upsampling layers, which will help us to actually, of course, increase the image resolution. Now, at the end, this deconvolutional neural network should output a very similar image to what was given as input. Of course, not exactly the same, because again, it's impossible to do exact and such intense compression. You can only compress so much. That would lead to information loss if we're going to such a small encoding. However, again, it is completely possible to create a very naive autoencoder this way, which compresses your image. But the reason I'm making this video is this will serve as it'll serve as a base, because in the next two videos, I'm going to be showing you how to use this autoencoder technology to do amazing things, such as neural machine translation to convert from one language to another, English to French or French to English, and how you can train a neural network for image super resolution. It's going to be really interesting, but for now, let's take a look at how you can actually take an image, super compress it with a convolutional neural network, and decode it with a deconvolutional neural network. In this case, I'll be using a simple convolutional neural network over here as well. However, Keras does provide support for deconvolutional neural networks. And today, I'll be showing you how to actually implement this on the MNIST 0 to 10 or 0 to 9 digits data set. But now let's get over to the coding part where I'll show you how exactly you can actually implement this autoencoder with Keras. Let's get to it. Alright, so welcome back to the Mac part. Now I'm going to be showing you how you can actually implement this autoencoder system. Let's take a look. Now what I'm going to do over here is I'm going to switch over to the code. I'm going to make this a little bigger for you. Now as you can see, this is the code that powers the autoencoder system. Now as you can see, of course, it starts off with our simple imports. In this case, the imports being, of course, SciPy in order to do the data conversion. Of course, we're going to be using NumPy. This is just generally for our arrays and arithmetic. We're going to be using the MNIST dataset that comes with Keras. We're going to be using the following layers today. In fact, we actually do not need batch normalization. We're going to be using the functional model type. We're going to be using the image from Pillow. And of course, we're going to be using the toCategorical function from the utilities inside of Keras. Now, of course, this image is going to be 28 by 28 in terms of size, and then we have some generic code that loads up the MNIST data, converts it to categorical output, and then, of course, reshapes it to work with Tiano, and then we just do divide equals 255 in order to make it from a 0 to 1 scale instead of 1 to 255 scale so that the neural network can understand the data properly. After that, what happens is we declare our input layer. The input layer takes in the input shape, and then we connect to it the encoding functions. Now, the encoding layers will actually take the image and convert them to a small encoded vector. And this vector will represent the actual image. However, this vector is not actually an image. It just represents what the image contains in fewer pixels than the actual image itself. It's basically trying to do lossy compression by taking an image, really scaling it down, and then scaling it back up while preserving quality. Of course, though, X over here is now equal to the model that actually encodes the input image. And then we set it to another model, and this model will actually decode that image back to its full-sized representation. Now, luckily with MNIST, we're only working with grayscale images, and so we don't need to worry about 3 different channels in our code or anything of that sort. We only have this one channel at the end here. Remember, if you were working with a RGB image, at the end you would have a 3 here, because of course you have R, G, and B channels. However, we only have one image channel here. Next, though, we actually set the model to the new model. We create a model and we give it the input layer and the output layer being X in this case. We print out a summary and then we compile it with a binary cross-entropy loss and an atom optimizer. After that, I run the fit function with xtrain and xtrain as the ytrain. Now, why is this? Because the thing is, we do not need these ytrain and ytest variables. Now, the reason we don't need them is because ytrain and ytest contain the actual outputs of whether this image contained a 7 or a 6 or a 5 or a 3 or any other number. However, this is useless information because all we want to do is learn how to compress and decompress images via neural networks. So we can practically discard ytrain and ytest. We only need xtrain and xtrain and xtest and xtest for validation data. We're going to be using a 32 batch size and running one epoch only. We're going to save the model as normal.h5 since this is a normal autoencoder. And after that, if I had already created a model, I would be loading weights instead of saving weights. However, I do not currently have a model, which is why this is commented out. After that, what I do is I take the first element in the xtest array. Remember, this will give us a sample that the neural network has never seen. It has only been tested on before. And so what I'm going to do from there is actually run that test sample through the neural network model. I'll then do some post-processing on the prediction of the model and the original sample that was given into the model, and I'll save both out to my disk. Now, the input that we gave to the model will be saved as input normal.png, and the output that came from the model will be saved as output normal.png. And so in theory, what should happen is we should be able to give it an image, and this image is of a digit from 0 to 9. And so that will be saved to input normal.png. This is the image that we give it. Then what happens is the neural network model will take it, compress it, decompress it, stretch it back over, and then once it's done, and once it has a full-sized image, it should save it back to the disk at output normal.png. That is how the model works. Let's test it out now. Now, of course, though, I don't have a pre-trained model. However, what I can do now is I can actually go ahead and run Python autoencoder.py. I'm going to run the script. As you can see, it prints out that it's using a TNO backend, and it should also print out the model summary here. It has given me the model summary. Give it just a moment, and as you can see, it's now training the model. This will take around 100 seconds, so instead of me boring you watching this model train, I think it would be better if we speed up this clip. Let's speed it up now. Alright, so as you can see, our model is now done training. Now, in fact, what has happened is it's taken the training data, it's actually trained for 112 seconds, and after that what it did is it gave us a loss value. That's 0.1017, which is relatively low. You can also see that it worked on the validation data that we gave it and gave us a validation loss, and this is 0.0753. Again, very, very low. However, we can do better. But instead of me training for more epochs, let's take a look at the results we've already gotten. Now what I'm going to do in Atom is I'm actually going to open up the input image, and I'm going to scale it up. Now there's no surprise here, this is just a regular 7, right? So as you can see, we just have this 7, right? It's a little bit crooked over here, there's some extra pixels down here, but for the most part, I mean, it's a perfect 7, just hand-drawn 7 by a regular human. However, what is really, really fascinating is when I open up the output image, look at the similarity in the image. That 7 is located almost exactly where the 7 in the input image is. Again, this is the output, this is the input. This is the input image, this is the output image. It is that similar. In fact, you can actually see that the quality of the 7 has increased in the output image. Why is this? It's because whenever it took a look at this image, it saw, hey, this is really looking like a 7. And so what it did is it called upon its earlier knowledge of other 7s that it's seen in the world. And it said, usually they are drawn like this. It has generalized so nicely that you can actually see that it's filling in those details and properly understands what a 7 looks like. In this case, it's only really preserving the position and the size of the 7. And of course, some of the more minute details are being saved or discarded, and then recreated into this masterpiece of a 7. However, this is still something that machine learning can do if you give it enough time. How about we do something that's even more fascinating? Let's take a look at denoising autoencoders. Now, this is something I am really excited about. Why? It's because you can give it noised up data. This includes anything like audio, images, really anything that has noise in it. And you can denoise it almost perfectly. Let's take a look. Now, as you can see, I'm going to switch over to this Python file here. This Python file contains something called a denoising autoencoder. I'm going to scroll up, as you can see, almost the same imports. We've got the same image pre-processing script. However, after that, I have some code, and I will be linking to this code down in the description below. I actually got this from the official Keras blog, and this actually adds extra noise to the data itself. And so now we actually have two different sets of data. We have one data, which is exactly the same as the second one, however, it has extra noise in it. And the next one is just regular data that does not have noise. And our neural network's job is to find out patterns in the the noised and denoised images and try and recreate or decompress into non-noisy images. And so as you can see, we've got the same sort of model here, we've got the same compiling and fitting, except there's one difference in when you actually fit the model. This time, instead of doing xtrain and xtrain, we do xtrain noisy as the input data, and xtrain, which is the regular data, as the output data. Apart from that, we want the batch size to be 32, epochs to be 1. We don't need it to be 1 verbose though, because that wouldn't print anything out. And of course, we just want the same validation data of xtrain noisy and xtest, or xtest noisy and xtest. Then we save this model as noise.h5, and then we have very, very similar code here to actually test out the model. We save the very first image, or the very first test sample of the model, as input noise.png. This is the image that has a lot of noise. And then we save the output as output noise.png. This is the image that does not have noise because the neural network model removes that noise from the image itself. Now let's take a look at how this works with a live demo of it in action. Now in order to do this though, we actually have to run that Python script. Again though, once it prints out the model summary, we're going to have to wait for it to generalize and train. So let's just give that around 100 seconds again, and I will be back in 100 seconds. Let's speed up the clip. Alright, so as you can see, the model is now about to be done training it as at 0 ETA. It's currently doing its validation, and as you can see, our loss is a little bit higher. Why? Because we're using the same model. That's, it's quite deep. It's a convolutional autoencoder. We're only running 1 epoch, though. We're only training with 60,000 samples. And, of course, we have a way more complicated task. And this task is to actually denoise a really heavily noised image. But let's take a look at the results. Now let's switch back over to my Atom editor here, and let's take a look at the input first. This is the input noise. Now, even as a human, this might take you a second to actually find out what's inside of this image. If you squint, you can see it quite easily, though. I'm squinting right now, and I can see this sort of like little, shadow of a 7 with tons of noise around it, though. So I can see that 7 there, that's for sure. However, like for example here, if you take a look, a lot of those pixels are really noised up. They're really just at this point, you cannot very much tell that they're part of the 7 over here especially. However, when I go to the output, look at the output of the model. That is simply stunning, really. Look at the deep learning capability. Not only did it remove the noise, it hallucinated realistic details into the 7. You can tell that it's a little bit thinner here than the rest of the line. Why is that? That's because this over here was almost completely corrupted by the noise. But the deep learning model realized that look at the strong signal over here. And what it did is it hallucinated that detail right back into the 7. Just like that. And that is how convolutional autoencoders work. That was a simple example of autoencoders in action. Thank you very much, everyone, for joining in today. Hope you enjoyed this tutorial. Thank you very much for joining. Apart from that, if you have any more questions, suggestions, or feedback, please leave them down in the comment section below. Email them to me at tadgymani@gmail.com, or you can tweet them to me at tadgymani. Leave a like down below if you really like this video. Maybe share it if you believe this could help out anyone else you know, like your friends or family. But apart from that, though, again, if you really like my content and you want to see more of it, please do consider subscribing to my YouTube channel as well, as it really does help out a lot. And apart from that, turn on notifications if you'd like to be notified whenever I release new content. Thank you very much, everyone, for joining in today. That's going to be all for this tutorial. Really hope you enjoyed. I believe the results were stunning with deep learning. Thank you. Goodbye.